Our next speaker is Anastasia Kisil from the University of Manchester, and she'll be speaking on recycling solutions for wave diffraction problems. All yours.
Thank you, Mike. So I'm going to first motivate this talk, and there's 4 motivating questions. So first of all, if we have a family of some kind of equations, and we want to find the solution, ultimately, we usually have 2 routes to do it. We either have an analytic route to do it, or we have a numerical route to do it. If we have an analytic formula for the solution, it's usually very easy to decouple the kind of where the forcing, what the forcing does to the equation. If we have a numerical solver, usually it's impossible to tell what the solution will look if we change the forcing, right? So I'm thinking in terms of a wave scattering problem. We change some parameter in it. If you want to do a console simulation, you'll have to rerun the whole thing again if you change something, right? In an analytic solution, one of the main advantages is that you kind of understand the structure of the problem, and then you know what changes when you change certain things. So we will consider whether we can write a solution in terms of 2 parts. First one, which is dependent on the parameter, and second one, which is independent of parameter. And ideally, we would like the one which is dependent on the parameter to be an easier problem than the one which is independent of the parameter. So those are 2 kind of general questions, and more specifically, we'll be talking about what is embedding formula in diffraction. And one observation is that a lot of problems which you can formulate in terms of Wiener-Hopf can also be tackled with the embedding formula. And the overall arching question of this talk is why. Why is that true? So here we'll start with a motivating example. So this is a baby example. We can all solve this explicitly. So if we start with an equation at the top, this we treat as a forcing term, F. And suppose we want to solve loads of those equations for different F. What we can do is we can split the solution into 2 parts. So this first part, which features F, but has an R, which is given here. So we solve a more difficult problem. We find R here, and once we found this R, we can then put this R into a simpler problem and compute that very fast for a lot of R. Okay, so if you look at this example, you're probably thinking this is a trivial example, and there's a number of ways to show why this is true, and the easiest way to show why this is true is to go into Fourier space. If you Fourier transform all of this, this just becomes algebra. And this is one of the kind of takeaways from this talk, is that going to Fourier transform makes everything much easier. Okay, so now we're going to go and introduce what we mean by embedding. And I'm just going to use the board. So usually, when consider embedding in diffraction, you have some kind of scatterer. We'll look at this. And the family of equations come from different incidents. So you might want to compute what happens if you change the incident wave, the angle of the incident wave. And if you do it somehow naively, experimentally, you might not think there's any reason to think there's any connection between those solutions. But Williams in 1982 has shown that all solutions to this problem in the far field can be expressed in terms of a grazing incident field. So if you somehow compute this solution, you can have a good insight on what the solutions look like. And later on, Porter, so that the example I gave on the previous slide is from one of his papers. He's worked on integral equation formulation and showed how an integral equation formulation can be used for different forcings. But the general idea of embedding is that we're not trying to solve the problem. So we're not solving the problem. All we're doing, we're expressing one solution in terms of other solutions to related problems. So that's what the aim of the game is. Okay, so now, since we're interested in Wiener-Hopf, we're going to, actually no, before we plunge to Wiener-Hopf, we're going to see, so in 2003, Kraster, Shanin, and Dubrovsky has derived a very systematic way of deriving such relationships. And it has 4 steps. And the first step is you start with a physical problem like this, where you have Helmholtz equation, and you apply an operator, and you choose the operator such that it still satisfies the Helmholtz, the solution. So you suppose the solution exists, first of all, and then you apply an operator to this solution such that the incident field is killed off, which kind of makes sense. Now, if you don't have the incidence field, then you can express it in terms of something which doesn't have incidence field. And instead of but the boundary condition is still preserved here, but the tip condition is no longer satisfied. So usually what we think about the tip condition is the condition that there's no sources here. But instead, this looks like a problem where you place a source near the tips here. So this might be a little bit abstract, but you're trying to solve the equation by first kind of killing off the wave and then seeing what goes wrong. And what goes wrong is the condition at the tip. So you define functions which have the same singularities at the tips, and then you do a combination of those functions here, so that now you have Helmholtz equation, all the boundary conditions are satisfied, including the tip condition. So now you know that the solution should be 0. There shouldn't be any field if you don't have any forcing and all the boundary conditions are satisfied and you have uniqueness of the solution. Okay, and that gives the weak form of the embedding. And then if we use the reciprocity theorem and go into the far field, we can obtain the strong form of the embedding theorem. And I'll talk a little bit more about that, but we'll mainly concentrate on the weak form of the embedding. Okay, so going into the Wiener-Hopf world, we're going to talk a little bit about the concept which has been introduced by Georgian Mathematical School and Garov. So we've seen a little bit about this already on Monday. So you have this notion of normal solutions. There's also fundamental solutions, and there's also canonical solutions. Those are 3 different words. You can go from one to another by kind of simple manipulation. So here we're going to go and concentrate on the normal solutions. So we're going to have a Wiener-Hopf equation. More generally, that works for a Riemann-Hilbert equation.
Press escape.
So what we're going to do is we're going to define solutions with no forcing. This is an n by n matrix K. So when we look for a solution, this will be a vector, an n by n vector minus an n by n vector plus. And what we can do is we can find different solutions, right? This solution is not unique. If we find n such solutions and arrange them in a matrix like this, so this would be an n by n matrix, this is a very useful matrix because what it does, so we have one condition. We want it not to be 0 anywhere on the whole complex plane. So that, in some sense, gives you a linear independence type condition. So what it does, it provides us with a way of writing down all the solutions to this homogeneous equation. So if we combine those linearly with a polynomial forcing, we get all the solutions. Okay, so that might be not very surprising, but what we're going to use here is the fact that those v's, when you combine it into x's here, so this matrix X also provides a factorization of our matrix. Okay, so this is our usual Wiener-Hopf system. We have our U minus, U plus, you have the K, and you have the forcing. As we all know, the most difficult part of solving a Wiener-Hopf system like this in matrix case is to do the factorization. We suppose that we have found n solutions to the homogeneous problem, and then we have our factorization like this. Once we have the factorization, it comes as no surprise that we can write the general solution in terms of the factors. So we've done just the usual stuff. We multiplied through and then separated pluses and minuses and so on. So here is what happens when you just do an additive splitting of the remaining term. Okay, and the claim is that this looks very similar to what we've seen on the first motivating slide, right? So if somehow we can compute, well, in a different way the x's, now this is just an integral, right? So the forcing is now just given by an integral. We split the problem into two parts. And how is that linked to the embedding problems? Well, in the special case when the forcing is a pole, or in general a polynomial, we know what to do for the additive splitting explicitly. So that's pole removal, so we can write down the formula for that, right? So instead of just having the Cauchy type integral, we can remove poles and we get something like this. So now we have the dependence, so the Z star has the angular dependence, the dependence on the instant field. The Z, the other functions are independent of the angle. So now we split the problem into two, the harder and the easier problem. And we also see, so let's see how this works in the particular example. So the particular example is this strip here. And what we want to do is we want to solve it using Wiener-Hopf. So, I mean, you've seen loads of formulations of this problem before. There's nothing surprising here. The only thing I want to say is something about directivity. So if you don't work in acoustics, basically if you want to look at the far field, so you want to draw a big circle around here, so the dependence on R can be factored out in this expression here, and you just have a function in terms of your incident field and your observation angle. And of course you have the tip condition, which once you go into Fourier space gives you the growth at infinity. Okay, so then we see our friend, and you've seen matrices of this type in Elena's talk, and you also I know a few of you work on similar things. You get matrix like that, and this is a very typical example of a Wiener-Hopf matrix which we can't factorize exactly. So we want to try to do something, and the something we're going to do is to try to derive this embedding formula instead. So we follow the procedure. So the procedure is we look at the homogeneous problem, and we say, suppose there are two solutions, like this, and we suppose that they are normal, and we also normalize it to have this particular behavior to infinity. Then in terms of those two solutions, we can write down explicitly what the general solution is. Okay? So those are constants, that's good. There's dependence on alpha. So this is what it's called, it's the weak form of embedding. So if we want to compare it to known results in embedding theory, we want to derive the strong form of embedding. So in order to do that, we need to go into the directivities. So we know that doing steepest descent, saddle points, that the directivities are given by the following formulas. So okay, so here the hard bit of this slide is to show that the solutions that we found in the previous slide, the V's, correspond to the physical problems defined by placing sources of this. So, but from the point of view of this method, that's not important. What's important is the fact that we can express solutions in terms of each other. So what do we need to do? We have a formula. To get the far field, we need to put alpha equals to minus cos of theta. And the second thing we need to do is you notice that there's those functions evaluated at k star. And k star has a similar form. It has a k cos theta n. But of course, if you want to relate it to the functions up there, we want to change sign. And the symmetry of the Wiener-Hopf problem allows us to change the sign. So now we can express the solution entirely in terms of directivity. And you can see how this is, why this embedding formula is computationally very attractive, is if we want to compute some kind of, to draw some kind of plot, we'll generally have theta here and theta in here. And if you want to compute 1,000 points on this axis and 1,000 points on this axis, this would be 1,000 by 1,000 grid, which you want to calculate at every point. But instead, this is now expressed in terms of functions of one variable. So really, we'll be just calculating two functions like this. Okay, so this is the attractions of the embedding formula from the point of view of computation. But from our point of view, we've just checked that this Wiener-Hopf approach gives exactly the same formulas as the standard approach in terms of the operators. Okay, so there's another way of looking at it. So Biggs has also proposed a very similar but slightly different way of looking at it. So instead of considering point sources near the tips, he considered expressing solutions in terms of each other. So now, instead of having a set number of auxiliary problems, which you solve, and it forms your kind of basis functions, you solve a few of the usual physical problems and then express all the other solutions. So for the example here, that's what Williams did. He solved one problem like this and then expressed all the other solutions in terms of this one physical problem. For more complicated problems, you'll have to have more solutions. So you might need to compute some different ones from different angles. And an interesting question is, how many of them would you need to compute for which geometries? So let's just go through the method as well. So first of all, you do exactly the same thing. So somehow you need to get rid of the incident field. So you want to get a problem which has no incident field. So you apply this operator, which annihilates your incident field. But now, what you do is you choose some set of problems, as I talked before, and you have to choose enough of them for then to be able to do this. So what you're trying to do is you're trying to kill off the bad behavior at the tip, right? Maybe I should, yeah. So now, again, you apply uniqueness theorem because you have an equation which has no incident field and satisfies all the boundary condition. Again, you should get 0. And the last step is also similar. You use reciprocity, although reciprocity looks slightly different in this context, and you obtain the strong embedding formula. Okay, so let's try to do exactly the same in the Wiener-Hopf setting for the plane waves. So now the procedure looks very, very simple. What we do is we look at the Wiener-Hopf equation, we factorize but we don't actually do an explicit factorization. We just say, suppose such a factorization exists. We multiply through by this, right? And then what we're trying to do is slightly different. So instead of using pole removal, we're going to multiply through by the polynomial, which we have, right? So now the only singularities of this equation come from the poles of pi. So that's our polynomial, might have poles in the lower half plane. What we do, we multiply through by this polynomial. So this is very similar to introducing those singular solutions. So applying an operator to your solution makes these singularities appear here. So now in the Fourier space, when we multiply it through by p, we introduce singularity at infinity, so we introduce growth at infinity. We introduce this growth at infinity, and if we apply Liouville's theorem to this, so instead of getting the usual either 0 or constant, we're going to get a polynomial of degree, whatever the growth at infinity is going to be increased by the degree of p, right? So what we can do is we can pick constants a, I to get rid of these polynomials, right? We can have linear combinations of such families of solution which will have no growth at infinity. And if we apply Liouville's theorem to this now, what we're going to get is we're going to get some kind of combination of the solutions equals to 0. So the claim is that this is a very similar procedure to what's happening in the physical plane, but it's happening in the Fourier plane, and it's entirely algebraic. So let me just give a more interesting example. So at the moment, I've only talked about this example when you taking a Fourier transform in this plane. So I've talked about one strip, but of course, if I increase the number of strips, nothing will change. We'll just increase the order of the matrix Wiener-Hopf, but we can do exactly the same. So here is slightly different. So here we have a wedge geometry. So by wedge geometry, I mean we can either have a real wedge, or we can have two strips, for example, which form at some angle. And we suppose that the angle that they make is rational. So if you do the usual transformations, so apply Laplace transform, you get an equation like this, which is not in the form of a Wiener-Hopf. We don't know what we want the plus and the minuses, and in order, this is all standard stuff, so in order to get a Wiener-Hopf equation, you have to have this transformation. And once you put this transformation, you have functions. You have this v with the z minus alpha and z plus alpha, and the analytic in the upper and lower half plane. So this is standard stuff. This is how you would deal with the wedge geometry using Wiener-Hopf stuff. Now, what I'm going to say is that how would you get an embedding formula for the wedge geometry? Things are slightly different. So here, we need to obtain some kind of relationship between those functions here. And the claim is that we need to multiply by this particular factor, qi, cos of z. The reason we're multiplying by this q factor is that we multiply that for the equation before the transformation. Once we do the transformation, going from z plane to alpha plane, this will correspond to this function, which you might recognize as the Chebyshev polynomial of the first kind. So you've seen Chebyshev polynomials in the Lena's talk. They pop up all the time. But what's important is that now we're multiplying by some polynomial. And the degree of the polynomial will depend on the angle which depends on P and Q, right? So I mean, this polynomial depends on Q. So now we're exactly in the same format as we had before. Okay, so that format is we can apply exactly the same procedure and get the embedding formula for it. Okay, so let me just quickly go to the comparisons. So what do we do differently? So instead of applying an operator, we multiply the Wiener-Hopf operators by some kind of polynomial. You can see the equivalence of those two things. So that's in the simple case. In the more complicated case, the operator was also linked to Chebyshev polynomials. We also see that the relationship between the homogeneous problem in Wiener-Hopf and the Green's functions are over singular solutions. And also we see that the behavior at the tip, which was used to get uniqueness in the physical field, now is substituted for having the behavior at infinity, which is used with Liouville's theorem. Okay, so just to draw the conclusions, so embedding allows kind of a halfway house when you can't solve the Wiener-Hopf system, but you can still formulate the Wiener-Hopf system. You can do embedding, and if you've calculated what this Wiener-Hopf system is, then doing embedding is very simple, and that's partly what we were trying to do, is to show that actually you've done most of the work by deriving the Wiener-Hopf system, and now the embedding will fall out from there. So far we've shown more or less all known examples in very simple geometries, and of course the next step would be to go into more interesting Wiener-Hopf systems, and we've seen a number of interesting Wiener-Hopf systems in the talks today and yesterday, and those ones we would talk about later. Thank you.
Thank you. Okay, so we have time for a couple of quick questions.
Okay.
Yeah.
So how about Maluzhin's problem? Your technique recovers his solution?
So I mean we've looked at the wedge, which is just perfect conditions. We've not really looked at the more complicated boundary conditions on the wedge, but there's no reason. If you can formulate it in a Hopf problem, getting the embedding is very simple from there.
No, but the answer is yes or no?
Maybe.
Because then we either can confirm. Vito then wrote a paper 2004. He used art cosine and he recovered Maluzhin's solution using matrix.
So as I said, we're not writing down solutions. So embedding is not about writing down solutions. It's about finding relationship between different solutions.
We had done something similar in 2007, where we have used matrix factorization with the freedom factorization, with the integral representation, and there are some connections that can be exploited in your framework.
Okay. Yeah. Cool. We should talk about it.
One more quick question.
You assumed that your matrix kernel has a Wiener-Hopf factorization, but the question is, how do you check this? For instance, in those triangular matrices where the diagonal elements are oscillatory, it may happen that the homogeneous equation has infinitely many solutions, and then there is no Wiener-Hopf factorization. In your case, where the non-diagonal element is a square root, have you checked that there exists a Wiener-Hopf factorization?
The answer is no. So this is an assumption, is that if you have a physically motivated problem which has a solution, then you can write it in terms of Wiener-Hopf, then there should be a factorization. So it doesn't. We've not proved that the solution exists. No. And in general, if you want to use this rigorously, you want to show that such systems have the factorization. Yes.
I think that's a good point to go for coffee. Okay, so can we thank Anastasia?
Can I just say a few organizational things? So, first of all, Han has already introduced the conference in China, and I know less about this place, but I just want to say a few things about the practical aspects. So first of all, there's no website where you can just register for it. So if you're interested, please email one of us, and the 4 organizers are indeed all present at this conference. And I'll be very happy to add you to the conference. So we have obtained funding for 30 participants, and the funding includes 5 days accommodation and 5 days of meals. This is restricted, so basically what we would want to do is to find 30 people who are willing to do it. So there's 2 things I would ask. If you already confirmed you're coming and then decide that you don't want to come, please let us know as soon as possible. And if you haven't yet decided whether you want to come or not, but you want to be considered, please email me as soon as possible. Once this is over, Gennady and I and the rest of us will try our best to actually put a timetable together for it. In terms of promoting it, I can't compete with the nice video we saw. I can give a very out-of-date TripAdvisor information from Marco Polo, because Marco Polo has written the first traveler's notes, which got very famous, and he called Hangzhou the finest city in the world. So this is slightly out of date, but of course we're at the conference, so instead of saying it's out of date, this is classical information. So this is indeed the best city of the world according to classical knowledge. This is also situated in a very nice institute, and this is information from the website. I haven't checked it, but apparently the best place to visit is the West Lakes, and we're situated in the second best place, which is the sister to West Lakes, and there's very nice nature around and so on. And the second, so that's first organizational, and the second organizational thing I want to mention is that we have some networking / collaboration event after this coffee break. So please, if you're interested, what we're going to do is we're going to try to get everyone to know everyone a bit more closely. We're going to have a few tables, we're going to move people around, and we're going to ask them to discuss different questions. And we have very capable people, John and David, who are going to help move the discussions. Because in academia, some people are better at networking than others. And I think we've chosen the kind of people that are the best at networking to teach everyone else how this should be done. Okay, thank you.